Hello students, we are starting our today's chemistry class. Today is 20th September 2023. Let us start now. Now we will discuss about we have given an example of orthorhydrobenzene, metahydrobenzene and tetrahydrobenzene. And my question is, what is the increasing order of these three organic compounds? Okay. So first we are starting with orthorhydrobenzene. This is orthorhydrobenzene, you know. Here this bond moment and this bond moment projected like this. Okay. That means these two are acting as two vectors maintaining the angle of 60 degrees. And from this formula we get the result. That means the resultant dipole moment R equals to root over 3. Okay? You understand what I am saying? Here, two bond moment. This is one bond moment, and this is another bond moment. Acts with the angle of 120 degrees. That's why if we draw the parallelogram, it will be projected towards this. That means if it is P, the resultant will be from this formula R equals to P. You understand? Next, you see the paradihydrobenzene. This is paradihydrobenzene, where one bond acts in this angle and another bond moment acts in this angle. Their angle is 180 degrees. Okay. So these oppose. These two oppose each other, and the result is obviously 0. So if we compare mu of ortho, mu of meta, and mu of para, the increasing order will be mu of para, then mu of meta, and then mu of ortho. That means the orthodipropylbenzene has the highest dipole moment among the three organic dichlorobenzenes. Okay, what is dipole moment? Look at the board. If we draw the structure of simply hydrogen chloride, the dipole moment is a resultant of all the bond moments in a molecule. Okay. So here is one chemical bond. So obviously, as chlorine is more electron than hydrogen, the bond moment acts in this direction. And you know, as chlorine is more electronegative than hydrogen, chlorine gets a slight negative charge and hydrogen gets a slight positive charge. So the dipole moment mu equals to the charge accumulated on the atoms, and you know the charge is equal if the charge Q and the bond length is D, then the dipole will be the product of Q and D. Okay. So it has some dipole moment. So in this case, mu is not equal to 0. It has some value. If we consider another molecule like carbon dioxide, what is the structure of carbon dioxide? We know this is a linear structure. Okay? If the structure is linear, one bond moment acts towards this side and another bond moment acts towards this. We know oxygen is more electron than carbon. That's why negative charge develops on this oxygen atom and also in this oxygen atom, and positive charge accumulated on the central carbon atom. So, what is the dipole moment? One acts towards this is the point, and one acts towards this. These two are in the same amount. So, mu is equal to 0 here. Okay. So, carbon dioxide is a non-polar compound. Now, obviously, hydrogen chloride is a polar compound. Okay? If we take another example, suppose H2. What is the case of H2? These two are two lone electron pairs and two hydrogen atoms within the angle of 104 degree 20 degree. You know the structure, the electron pair geometry of H2 is tetrahedral, but the structure is, molecular structure is angular. Okay. The lone pair produces a moment, this reaction, this lone pair produces a moment, this reaction, this OH bond produces bond moment, this reaction, and this bond moment, this reaction. As we result of oxygen more active than hydrogen. So these two, the resultant of these two bond moments acts as this. That means these two bond moments, the resultant of these two bond moments acts in this direction, and the moments produced due to the lone electron pairs also acts in this direction. So the resultant is too high. Okay. So H2 has very high electron moment, and obviously mu is equal to 0, and it has very high dipole moment. Okay. So obviously it is a polar compound. If you take another example of sulfur dioxide, look at the structure. Okay. This is sulfur dioxide. It has one lone electron pair. This bond moment acts towards this angle, and this bond moment acts in this direction. Bond moment due to lone electron pair acts in the opposite direction. So the resultant of these two bond moments is like this, plus is like this. The resultant is to some extent less than I expected reactant is this. So obviously mu is not equal to 0. Therefore, it is also a polar compound. Okay. If we take the another example of ammonia, you see, what is ammonia? It is one bromine plus, and we know the electron pair geometry of ammonia is tetrahedral, but the molecular shape is trigonal pyramidal. In this case, these bond moments are acting like this, and this moment due to low electron pair also in the upward direction. So the resultant of three H-N bond moments is looking like this, plus the moment due to low electron pair is this. Therefore, the resultant will be, as expected, is a high. Okay, so mu of NH3 is not equal to 0, and this is also a polar compound, and it is very high dipole moment. Okay, if we compare with NH3, what will happen? Okay, you know, fluorine is more electronegative than nitrogen. So, in this case, the bond moment is acting towards this, opposite tube, in the case of NH3. Okay, but the moment due to low electron pair acts towards upward direction. That's why it will be for low electron pair, and it is for three bond moments. That means the resultant of three bond moments, and counting the two factors, the resultant dipole will be too much less than the case of NH3. So, mu of NH3 is obviously less than, very less than mu of NH3. Okay, and obviously mu is not equal to 0 here. That means mu of NH3 and it has less dipole moment. Okay, and it also a polar compound. Come to the next section of our class. Okay, we will now discuss the dichroism of carbon monoxide. You know, oxygen has two lone electron pairs. One is your p orbital and another is sp hydrogen orbital. And this carbon has one hydrogen orbital, that is sp hydrogen orbital, and this orbital is vacant. This is vacant orbital. Okay. Here, this lone electron pair donates to the vacant orbital of carbon atom, thereby forming a pi dative bond. Which bond? Pi dative bond. You know, henceforth, we get the structure like this, plus minus the lone pair. The bond moment arises due to two bonds this direction. But for pyritic bond, that is back bonding, acts in this direction. This is also directed towards this, and this lone pair, the moment due to this lone pair directed towards this. So, here are several factors. Counting all these factors, we get the result like this. Look at the result. There are 1, 2, another 1, another 2. Okay. So resultant dipole is very, very small towards the oxygen atom from the carbon atom. So the dipole moment of carbon monoxide is very, very small than as expected normally. Okay. This is all about the dipole moment of carbon monoxide. We will now discuss about the comparative dipole moments of orthonitro-methylbenzene, metanitro-methylbenzene, and paranitro-methylbenzene. Look at the structure now. This is orthonitro-methylbenzene. This is metanitro-methylbenzene. Which is also written as only N. And this is paranitro-methylbenzene. We have written all three structures of okay. What will happen next? The moment due to methyl group, due to inductive effect, through this bond, moment directed towards this direction. For nitro group, as it is a electron withdrawn group, moment acts in this direction. So the resultant vector comes from in this direction, and you will get the dipole moment of orthonitro-methylbenzene. Okay. What about metanitro-methylbenzene? Similarly, this is in this direction, this is in this direction. Okay. So this acts like this, acts like this. At angle is 60 degree, but here angle is 120 degree. But what happens here? Both act in the same direction, So the resultant drag moment will be highest in this case. In this case, resultant acts in this direction. Okay? So mu of meta is highest, greater than mu of ortho, greater than mu of para is highest, and then 1.275 angstrom a minute. Okay, that means 1.275 into 10 to the power minus 8. Okay, that means 6.12 into 10 to the power minus 18 SU centimeter, which is equal to 6.12 dBi. But unfortunately, we observe the mu observed value is only 1.03 dBi. Therefore, the percentage of ionic character equals to 1.03 dBi divided by 6.12 dBi into 100%. That is equals to 16.83%, which is approximately known as 17%. So, the HCl bond, this is the covalent bond, but it has some ionic character. To some extent, that means the ionic character of 17%. This is for our today's class. All the viewers are welcome to my chemistry class always. We are opening a coaching center. The branch of this coaching center, that means the Ptolemaic Coaching Center for Chemistry. We are not only studying chemistry, but all these subjects, all 4 subjects, PCB and PCM. Okay, see you in Kolkata at near Kavi Nazrul Metro Station, L58, Bospada Road, Kolkata, 7,84,000. See you there. Okay, all the students are welcome to my new branch at Kolkata. It is very near to Kavi Nazrul Metro Station. Only 5 minutes to go to the Educational Institute. So see you there. That's all for this class. Okay. Welcome always to my chemistry class at Ptolemaic Coaching Center for Chemistry.